welcome to the class. I will tell you another phenomenon, it is very important phenomenon with cryptand. Okay? When in a cryptand, when you put a metal ion goes here inside. Why is that? Because of cryptand effect, right? Because of cryptand effect, that is nothing but it is more stable, like macrocyclic effect, like cryptand effect. So, this is a cartoon. So, because of cryptand effect, metal goes inside. It was we wanted to have system that how can we put this metal ion outside? Can we put the metal ion outside and then bring it again inside? That means bahar bhitar karenge isko. That metal ion will go outside and come inside. Then it will be a dynamic system. Then again also it is very, very important. Okay? It will give very important properties. So, how to do that? One way to do that would be reducing the donor ability of these nitrogens. That is what we thought, and we were right on the money, absolutely right. That was the reason. If we can reduce the electron donating ability of this nitrogen towards the metal, then can we force the metal ion to bind outside? Okay? For that reason, what we did, we put to this nitrogen, we put an electron withdrawing compound. For example, 2,4-dinitrobenzene. 2,4-dinitrobenzene is a very strongly electron withdrawing group. Okay. If you put 1, 2 and 3, up to 3 we can put, if we put all 3, or if we substitute NH by this 2,4-dinitrobenzene moiety, then we find that this cryptand has lost its metal binding ability. So, therefore, we played with that and eventually we found that when we have mono substituted, then we can go from outside, then metal can bind outside, from outside. Okay? We have X-ray structure also that to prove it. And what happens? Another important part. You see, you have say metal can have a perchlorate salt, BF4 salt, okay, or metal can have chloride, bromide, etc., or thiocyanate, azide. So, these are called coordinating anions. These anions have power to coordinate metal ion, and perchlorate, BF4 are usually non-coordinating. BF4 is very good as a non-coordinating anion, because that leaves aside, does not bother anything. Perchlorate sometimes bind metal ion. Nevertheless, both of them are non-coordinating anions, and these are coordinating anions they called. All right. So, this is one knowledge. Second knowledge is, if we make monosubstituted with dinitrobenzene, that is an electron withdrawing group, that means it is withdrawing this lone pair towards itself. because it attracts electron pair, electron cloud. So, it will be coming towards the dinitrobenzene moiety. Therefore, in presence of perchlorate or BF4 which are non-coordinating, the metal binds here somehow, metal binds here to strongly and this is weakly. Okay, weakly, still it has no choice but to bind here. But to that, if we add say thiocyanate or potassium thiocyanate or sodium chloride, potassium bromide, etc., which are coordinating anion, then the metal comes out here. Metal comes out. So, it binds here outside and then maybe say chloride or bromide. So, this is a property, this is nothing but coordination chemistry. Okay. So, with that knowledge, here we have made another way of having reversible fluorescence. We have this compound, this is a fluorophore, and what is the characteristic of this fluorophore? Let us call it diaza fluorophore. This fluorophore is electron withdrawing, it withdraws electrons. So, when we react this with cadmium perchlorate, okay, perchlorate is non-coordinating anion. So, therefore, when cadmium goes in, okay, we have done this with copper and etc., but cadmium works very good. So, that is why you have put with cadmium. So, cadmium goes here when it is perchlorate, and when cadmium goes here, because cadmium and this nitrogen is very close, so it has to bind, and because it is bind, PET is blocked. PET is blocked, so I will see high fluorescence. Here there is no metal, so when I excite it, PET takes place, so low fluorescence or no fluorescence. So, low fluorescence, high fluorescence. Now, if you put potassium thiocyanate, which is a coordinating, thiocyanate is a coordinating anion. If you put thiocyanate, then it comes out. I have put like this, comes out. Metal goes in and comes out also, depending upon anion. This is anion controlled translocation of metal ion in a cryptand. So, it translocates out to outside, and when it comes outside, now if I excite it, if I excite this fluorophore, PET is on, so no fluorescence. Here is also, when I excite this fluorophore, PET is on and low fluorescence. But in this case, but again we give silver tetrafluoroborate. So, silver thiocyanate comes out. So, thiocyanate goes out and BF4 is hanging there, which is a very low coordinating, almost no coordinating ability. So, cadmium goes in again, because cadmium likes 1, 2, 3 and 4, it has to have its 4 donors. Outside it gets 1, 2, 3 and this 4th. So, outside it can get 4th if this is a coordinating anion. So, this is another way of having reversible fluorescence with playing with the counter anions. Okay. All right. So, enough of this reversibility. Now, I will talk to you about chemical computer. Okay. Today's computers that we have, computers are based on silicon technology, okay, silicon semiconductors. Our present day computers are silicon semiconductors, and earlier the computer was very big, it used to do only calculation, but now since with passage of time more and more sophisticated computers have come out. Nowadays we can have very small computers can do many jobs. Why? Because my things are coming down slowly, slowly, slowly coming. So, earlier I just get a earlier you must have seen something like this. Isn't it? So, you have seen like these chips, we call it chips, and here you have circuit and all that. So, this is a chip, computer chip. Earlier this computer chip used to be this big. So, the computer will be very big, all right. There is a first computer called Neumann machine. So, one Neumann machine is kept in University of Chicago. I visited there. So, that is a big hall. In the big hall, and some couple of guys have to turn around the wheel. Everything is made up of stainless steel. So, made up of wheel, and then something the levers will go here and there, and maybe it will become a positive. So, 2 plus 2, to have 2 plus 2, several guys have to do this thing, but still it will give good results, accurate results. So, that is just an exhibition, that is junk right now, all right. But since then we have computers very small. Earlier computer center has to be spotless, okay. They will not allow people to come with shoes and all that. You open your shoes and use a special socks and then get in, no dust, it will not work. But nowadays we have laptop everywhere. Laptop is just throwing in the, you are working in the laptops outside, lots of dust, nothing, but nothing happens, it will not happen. So, with the passage of time, computer has become smaller and smaller and smaller. That is called Moore's law. Moore is Chief Executive Officer of Intel Corporation, US Intel chips. So, he is predicted that every 2 years the chip will be half. Now, here I am coming. So, this is called top down approach. What is present right now, it is called top down approach, top down approach. Okay. It is called top down approach. So, there let us take a, we can go to smaller and smaller and smaller, but can we keep on going to smaller and smaller? That is what I am going to discuss. Okay. Suppose you have a computer chip, if you look at carefully, you will find like this. Maybe here is here, so you can find like this. Okay, something like that, you have seen that, and that thing actually is made by a machine. they actually form a group, and sometimes they put gold there, gold, pure gold. That is why they can be, but there is very small amount. So, Intel Corporation, they will make it. Okay. So, now these things are there. So many other ways, and it is a golden color because it is gold. All right. And why gold? Because gold is very good conductor. So, it goes. So, if I have to make top down, earlier times it was very big. So, वो तो आसानी है, it was not very difficult. We could make these things and then fill it with gold and my chip is made. But as it going down slowly, fabrication is becoming more and more difficult. Okay. That means, after certain time we will face problem in fabrication. Okay. So, difficulty in fabrication. There will be difficulty in fabrication, that is one point as we go down. Number 2, as we go down, then what will happen? Smaller and smaller. So, these lines will be very close. Okay. Let's write. These lines will be very close to each other. They will be very close to each other. And what happens through these lines? Electrons flow very fast. Electrons flow and we get a positive, though 2 into 2 becomes 4. So, for that 2 into 2 to become 4, electrons has to move very fast. If electron is moving this way, that way, then what happens? Movement of electron will make it hot. Okay. Sometimes these computers are kept in liquid nitrogen, kept sometimes to cool it. It generates enormous amount of heat. Generates enormous amount of heat. Third point is, as we go to small and small, from classical domain we go to quantum domain. We reach quantum domain. So, like electron is a quantum particle. So, quantum domain, when we reach quantum domain, then Heisenberg uncertainty principle, uncertainty principle will be operational. What does this mean? Heisenberg uncertainty principle, that we cannot locate the position of electron if you know its velocity, or if you know its velocity accurately, we cannot if we locate the electron, then we cannot locate its velocity accurately or vice versa. If we know one accurately, other one will not be able to know accurately. So, there is uncertainty, okay, uncertainty about movement of electrons, all right, and that is Heisenberg's uncertainty principle. Number 4 problem. Number 4 problem. Quantum mechanical tunneling effect. I do not know whether I misspelled tunneling. Anyway, you write them, this is called tunneling, okay. My spelling may be wrong, I do not remember this thing. So, quantum mechanical tunneling effect will be operational. What is quantum mechanical tunneling effect? See, here is a circuit, here is another circuit, okay. Electron is supposed to go from here to here, but if it comes to quantum mechanical domain, so there is a resistance, high resistance, but sometimes instead of going this way, it can come here, it can come to the next jump, it is not supposed to go there. Tab kya ho? Then what will happen? The problem, we want multiplication, it will become division or something else, some problem. So, the computer will give errors all the time because of this quantum mechanical tunneling effect, all right. It instead of going this way, it can jump this circuit also. So, is going this way fine, but suddenly it instead of going this way, it comes here and goes started going again this way, then is all gone case. So, therefore, these are the some of the main difficulties associated with top down approach. That means, we cannot make a computer as small as our very small. Why do we want to make very small? Because if you make very small computers, then we will require less amount. If you make big computer, you will require more plastic, more metal, more everything. You cannot carry out here and there and all that. So, we want always our computer, my laptop would be maybe palm top, as small as possible. I can do anything with my, of course, we are now got that. I have a mobile which can do these calculations and many things, okay, like a laptop. But if I want to go further down, I cannot because of these difficulties. Therefore, a physicist called Richard Feynman. Richard Feynman is a physics professor, okay. He is no more. He was very smart. He said there is plenty of room at the bottom. He said there is plenty of room at the bottom. What does that mean? Bottom. If we come from नीचे से ऊपर, if we come from bottom up, okay, bottom means we have molecules. So, we take molecules, using these molecules we can build a heart of the computer functioning is called logic gate, okay, Boolean algebra. Boolean algebra, logic gate, these are fundamentals of a computer, heart of the computers. Okay. So, what we do now with molecules? How small is molecule? We cannot see it. Here is a computer I can see with my eye. So, it is a very big, is a giant actually. My mobile is a giant compared to molecule. A molecule we cannot see. To see a molecule, we cannot see even with a microscope. Okay, we cannot see. So small. To come from so small to my say small, very small mobile, it will take a long time, 1000 years. Okay. So, that means there is plenty of room, I can play with that, and this is called bottom up approach. This is called bottom up approach. So, therefore, we have two. We can give this, we can make this logic gate with my molecules. Logic gate means it will give bistable, and usually logic gate is usually we can use fluorescence. Fluorescence is very important because fluorescence lifetime is 10 to the power, typically 10 to the power minus 8 second. Fluorescence lifetime is 10 to the power minus 8 second, and fluorescence is very sensitive. So, this fluorescence on and off we can take bistable, a bistable switch, a bistable switch means one is off, we have a 0, and on means 1. So, it is a binary logic, like in a computer you have binary logic. So, with molecules we have this binary logic, and to connect this with other parts, like suppose this light is connected to the switch, okay, and when I put the switch on, the light coming on. So, that means this light is there, it is bistable, it is dark and light, and it is connected to the infrastructure. Infrastructure is what here? Electric wire. So, electric wire and then is a switch. Therefore, I can have molecular switch. Similarly, with chemicals I can have molecular switch, I can have molecular switch, I can have molecular wire. And bistable systems. Okay. With this I can go to make, with chemicals I can make computers. So, that is commonly called chemical computers. That is called chemical computer. Okay, so I stop here today. I will look at these bistable systems, or we can have logic gates in the next class. Thank you.